Hello and welcome everyone to the latest webinar from Oasys Software, the software house of Arrow. Today we are going to focus on nonlinear analysis options in GSA and hopefully show you what you can do with them. You'll be steered through the webinar by myself, Nick Nicknam, Business Development Manager at Oasys, and my colleague Peter Debney, who is our application specialist. Over to you, Peter.
Okay, thank you very much, Nick. Okay, so non-linear analysis. I'm going to start off with a few basics first of all, and just get us all up to speed. Obviously, to talk about non-linear analysis, we need to consider linear analysis and compare the two together. Linear analysis is based on a number of assumptions. Obviously, in reality, all structural behaviors are non-linear. It's just that some non-linears are behaviors are close enough to linear analysis to make little odds. So, for example, if this displacement and strain relationship is linear, it's good. If you've got small displacements, if you've got small strains, then the stress-strain relationship will be linear. And we're assuming that the equilibrium conditions, the balance of loads versus reactions, is all derived from the non-deformed geometry. So we don't take deflections into account when we're doing that. End results, linear results. And the thing to remember is that the results will be good if you've got small displacements and small strains. If you've got large displacements and large strains, your linear analysis results will not be accurate. You'll have results, but they won't be good results. And you need to spot this. On the other hand, if you've got large displacements, so your displacement strain relationship is not linear. If you've got elastic plastic, as in yielding materials, and if you've got large strain materials such as rubber, not used too much in building structures, but other than, well, as main structural members, not talking about bearings here. Any of those conditions apply, you need to do a non-linear analysis. End results are not linear, and the equilibrium is based on the deformed configuration. The end result, the cable forms in the catenary rather than assuming it still remains a straight line, and so on. Also to note, the structural responses may be path dependent. What this means is tension only, compression only elements will switch themselves on and off. Cables will go slack. Struts with gaps might separate, and so on. And analysis results are not combinable. You can't multiply results up and then add them together afterwards. You have to do that aspect of the analysis up front in the calculation. So let's start with geometric nonlinearity. Here we have a classic cantilever column under a vertical load P and a horizontal load Q. And when we say we're ignoring deformation when we establish equilibrium, that means that the vertical reaction F is exactly equal to the vertical load P. Likewise, the shear load Q is exactly equal, V is exactly equal to the load Q, and the moment is Q times the height. When we get on to geometric nonlinearity, we're assuming deformation, and the equilibrium is based on the deformed configuration. So the vertical and horizontal reactions are based on a combination of the loads P and Q, and the moment is Q times height plus the load P times the deflection delta. And this is where we get the expression of P delta analysis, because it takes into account the effects of that P delta effect causing additional moment. Let us look at that in action. Now, I have a GSA model already, which I'll go and open up. And in this model, okay, it's slightly different to the one in the diagram, because the horizontal load, the Q load, I've applied halfway up rather than at the top. I've also specified a static linear, static P delta, and a static nonlinear analysis for this. And notice we've got two of each, because we've actually in here got two loads. We've got a small load, 2 kilonewtons, and a large load of 2000 kilonewtons. Let's run those three analyses and see what we get. Let's look at the saved view to begin with. So here we have the save view, and this is the static linear small low results, and we see we get no shear or moment in the top part, and we get a moderate amount of moment and shear as you expect in the lower part. The large deflections, and note the deformation magnification is set to 1, so that is your actual deflection. The moment and shear are still directly proportional to this load here. The top load P has had no effect on them whatsoever. P delta analysis, small loads, exactly the same result as the linear. Large loads though, let me tuck that over to the side. Actually, then up again. Then we can see that we are getting moment and shear force in the upper section, and we're getting a lot more moment down at the base. Non-linear analysis, again, smaller, exactly the same as the linear, but with the non-linear we are getting much larger moments, including at the top part. Now you might be asking, what is the difference then between the P delta and the non-linear? Well, let's quick look at the individual. So A1, A3, and A5. These are the low load, small load, and you can see they are, the three cases are giving exactly the same results. A2, A4, A6, linear, P delta, and non-linear analysis. We can see that the displacements are now quite different, and whilst the vertical reactions might be the same, the moments at the base are quite different. Now, what's better between the linear and P delta? Well, let's look at the displacement at the top node, node 2. Node 2, node 1. Apology. We can see for the linear and P delta analysis, we're getting different reasonable horizontal displacement. The vertical displacement is both the same. Even though we're getting quite a lot of rotation on the structure, we're getting very little vertical movement. In fact, with that level of horizontal movement and so little actual shortening, strictly speaking, that means actually that section increases in length. Not good. Whereas with the non-linear, we're getting a full rotation, and as we expect, we get a much larger vertical movement. which suggests to me this is a much more trustworthy result. So P delta is okay for moderate displacements, but for the large displacement you do need to do the nonlinear analysis. In fact, I think nonlinear is generally used in preference to P delta as a general rule. They do come across it occasionally. Okay. We have a number of nonlinear elements in GSA. Struts and ties you may well be familiar with. These are bar elements which are compression only and tension only, so no moments on them. There's one called a sliding cable, sometimes referred to as just as a cable. This is a tension only chain element, which means the elements with the same property number need to be in a single chain line and have a curious ability that, or property that, the tension is constant all the way along the chain. Put another way, the words, the nodes along the length of the chain are free to move along the chain. Can produce some quite useful or unexpected results depending on whether you know what you're doing with them or not. There's also fabric elements, tension only 2D elements, which we're not covering today. We look at those in more detail in the form finding and fabric webinars. So let me call up a couple of example models for nonlinear elements. First of which is this model where we have just a single horizontal low load at the top, representing maybe wind or something like that, and in these brace bays we have bars in the first one, ties in the second, and struts in the last. If I then analyze this, we get displacement, and if I switch on the axial loads, as you expect, only one of the two ties and one of the two struts is activated. I mentioned about low path. You can see the low path is quite distinct down to this base. Now, if we were to change that analysis and a new analysis with low case 1, and then I'm going to second low case. Notice I'm double clicking to call the results up. I put minus low case 1 in there, and then analyze those two. We can see that the other low case, we get quite different results. In fact, let me show them both at once. That doesn't really help. I'll show the envelope as well. So the low path is totally dependent on the applied load, and thus it would be quite inappropriate to put a -1 factor onto this low case, because you just would not get those results. Oh, I almost forgot. A second model looks at cables. So on the left we have ties, on the right we have cables, and both have the same load on them. When we analyze this using a nonlinear analysis, which I've set up already, we get axial loads on the elements, which you'll note in the tie goes up there. In fact, let me switch on the resolved reactions as well. So the ties the load goes up the tie and then stops at that support. Whereas with cables, the load goes up around that support and back down to here, to the end of that chain of cable elements, giving quite different results. As these nodes along the chain act more like pulleys than fixed points, if you were to try doing a continuum model with the nodal loads along length, you will find they will slide into the middle, giving you a V-shaped deflection, not a continuum, which might not be what you want. But there are times when cables are very powerful and very useful. Material nonlinearity. With real engineering materials, steel, etc., you may get a linear portion of the stress-strain graph, and then a yield point, some plastic yielding, and then possibly some strain hardening. So this is how real materials might work, whereas with GSA we simplify it a bit, which means we get a totally elastic stress-strain relationship up to yielding points, and then a totally plastic behavior with no strain hardening, no yield limit. But there are ways to set those if you're using GSA to take the results into other programs like LS Dyna. So let's look at this in action. I've got the material model, and what I have here is a model where I've got a two-span beam, and with a linear and a non-linear analysis on there, and we will get some plastic hinges forming in there. I'll just analyze the linear model first, and I'll just run through the non-linear. The non-linear analysis, including element stiffness, won't take account. We haven't got axial load on here. Got non-linear load, and we'll then analyze that. We see we are getting some elements yielding and bending. And there is our deformed shape. That is quite exaggerated. Let me scale that back and unlock the scale. And we can see that the linear deflated shape is quite straight. The non-linear is not quite the same, and we do get different sets of results. So the linear analysis, we're getting much higher hogging. The non-linear, we actually got yielding at the support points, and then which means we then get much larger sagging moments. But we are on the verge of getting plastic hinges forming. I call up the stress results. And we can see for the linear analysis, we're getting way over capacity at the center. In the non-linear, we are apparently getting excessive stresses at the hinge in the middle. Reality is not quite correct, because the stress calculation is a post-processor, whilst the analysis is taking into account the elastic plastic zones moving across the elements. The results output here is just calculating what the edge stress will be. So it's not quite right in this particular case. but the underlying analysis is taking that into account. If we had pushed the load a bit further, we'd have had hinges forming mid-span as well, and the model would have collapsed all into the middle. Apart from static nonlinear analysis, we also have buckling analysis within GSA, and there are three main options really. There's linear buckling, which is eigenvalue or modal buckling, Dallard method. There is elastic nonlinear buckling, which takes into account displacement, and there's elastoplastic, which takes into account material plasticity. Now, the buckling analysis in GSA only does the first two if you're doing a buckling analysis, but if you're doing the non-linear static analysis, it will take into account material plasticity, but you're liable to get buckling anywhere within the structure, whereas with the member buckling, which we'll look at the moment, we just concentrate on particular areas that we're interested in. So linear buckling, as you know, when you apply an axial load on an element, its stiffness reduces, and what we're looking for is the load factor, the multiplier on the applied load, where the axial stiffnesses go to 0. Now obviously in a real structure there are many loads and many locations in the structure where that can happen, and so the modal analysis will give us multiple results. Things to note: that the shear load V has very little effect on the buckling load capacity. Not no effect, but little effect. And because the structure equilibrium is based on the undeformed shape, the modal shape is, well, the modal shape is correct, but the extent of the deformation is arbitrary. It's not giving the actual deformation. It's giving a normalized deformation, so the maximum deformation is set to 1 meter, and thus any sort of bending moments and so on that you calculate as part of the modal analysis will also be excessively large based on that deflection. With the non-linear member buckling, though, it's slightly different. Here, GSA will increment the loads and measure the deflection at each point up to final failure point, and thus the deflection is correct. But you only get the one set of results. How the results compare? Well, if you've got a linear buckling analysis, you just get a load. The displacement, as I mentioned, isn't really calculated. With the elastic nonlinear buckling, you'll get the buckling results which will approach, might even reach, the linear buckling analysis, but generally hopefully you'll come close. And if you take into account the material nonlinearity as well, it's quite likely that the load is quite a lot lower than the linear buckling analysis. All are useful. So let's go and call up a buckling load, which I'll take this column buckling model. And here we have a column with a minor axis support, pin at the bottom, grillage elements at the top, and whilst we could apply actual working loads, in this model I've chosen to apply a unit load, so the buckling load factor will be an axial capacity of the section. If we had working loads, then it would be more like a load factor against buckling against the applied loads. We look at the analysis themselves. So for modal buckling, I'm asking for a number of modes. I'm going to say 4 in this particular case. A load shift factor enables you to look at higher modes. Maybe the first 10 or 20 modes you're not interested in. You can use this shift factor to jump past them. Load factor cutoffs. Because the load factor can be negative in the results. Now, a negative load factor will indicate a load reversal. In this case, we're not going to get any tension buckling. But if the loads were applied differently, then that could be a possibility. Now, if you know that tension reversal cannot happen, you can set a lower boundary of 0 on that, so it'll ignore all load reversal bucklings. We've got our applied loads, number of iterations, conversion to criteria, and I will just look at the advanced features because there are a number of options in here. Make sure I'm taking into account the parallel processing of properties for maximum speed. Eigensolvers, I think we do default to the Jacobian method, but there is a new shifting and locking option for the eigensolver. Though if you've got an old model, the Jacobi iterations should be increased. Geometric stiffness, it will default to including all the terms, but I find it better to suppress the torsional terms in the GSA analysis. The lateral torsional that won't take into account warping and torsional, it can give some strange looking results. So personally, I often suppress those. If you're just interested in overall structural buckling rather than individual element buckling, then you can treat the beam elements as bars in the analysis. In this case, we do results. I'm going to only keep the displacements. I'm not interested in keeping the moments and so on, because I know they're inappropriate and I haven't got preload in this case. So let's analyze that. And we then get 4 sets of results, and we can see we're getting a buckling load of 642 for this first mode, which is major axis bend buckling. Mode 2, minor axis buckling, load factor of 819. Another minor axis buckling this time at the top, 1500, and then major axis buckling at nearly 1900. Just look at the results there, and we can see we're getting factors. Now, these factors are quite different, so I'm pretty sure that only this first mode will govern, which is this model here. And so what I'm going to do now is I'm going to run a member buckling, and I'm interested in elements 6, 7, 8, and 9, which I happened to have set up earlier. So we've got member buckling. 6, 7, 8, and 9. I'm going to add in my applied load, show deformation, and then finish. And this will then increment the loads up until failure point. And you see that once it starts to give, the analysis will slow down, or has slowed down. And then we're finished. And note it says plot axial force deflection curve to determine the buckling load capacity of the member. Now we do this, well, we could take these points here into Excel, but we've got the ability here in GSA to open up a chart view, nonlinear analysis, and then call up those results. And you can see that as the axial load increases, the displacement starts off small, and then the structure then gives. And if I switch on my coordinates nearest point, you can see we get a load factor of 632 kilonewtons, which is quite similar to 642 that we're getting from the linear analysis. For final design, we say, okay, this is our ultimate capacity, scale it back by an appropriate amount. Much about nonlinear cases and combinations, which I touched on earlier. If you're dealing with just linear analysis, you might not realize or spot that the load cases and analysis cases are actually separated. GSA by default will take the load cases where you apply the loads and create a single analysis case with the same name and the same number automatically when you just hit the analyze all button without defining analysis case. They are actually separate because in analysis cases you can do load factors and load combinations within the analysis, and the analysis case can be set up to give multiple results. Combinations themselves, you can combine multiple linear analyses together, but it's not appropriate to combine non-linear analyses together. And you can apply load factors if appropriate, and then you can envelope the results as you see fit. But it's another way. Let's look at the table view. So for linear analysis, you've got, let's say, dead load and load case 1. GSA will create analysis case 1, and then you can do the numerical calculations, combinations, including envelope. Whereas with the non-linear analysis, the combinations must be set up within the analysis task itself, because load paths can change because the equilibrium is based on the deformed geometry. That will change as you increase the load factors and so on, and therefore the non-linear analysis, you must set this up here, and then after that you can then envelope the various results but not combine them. GSA does these analyses by means of a method called dynamic relaxation. There's a similar method called Newton-Raphson, but we find that is okay for moderate deflections, but it's not good for the very large deflections that GSA can do. The way it works is that the structure is basically thought to be bouncing around. The stiffnesses are replaced by masses, connected by stiff elements, and as the structure moves, you have these sort of extreme points where the speeds reach 0, but the accelerations are maximum on them. So imagine this top point, the vertical load balanced out by the tension of these is at maximum downward force. This point down here, the upward force from the tension in these elements is far larger than the downward force, and so you're getting a net accelerations on these positions. What we're looking for is the equilibrium position, the point where the tension in these elements is balanced out by the applied force. And that point, being a dynamic method, is a point where it's got maximum speed but 0 acceleration. To help the models converge, we use damping in GSA. GS relaxes the solver within GSA. And with a couple of methods. The default method is viscous damping, which is a bit like putting the whole thing into oil. So the resistance is proportional to the velocity of the node. The faster the node is moving, the more resistance is applied to it. This can be a very quick method, or it can just completely fail to converge. Conversely, there is the kinetic damping, which is also known as artificial damping, and this looks for the points where the speeds are maximum, and the assumption is that these points are closest to the equilibrium position, and so it just takes the coordinates and just moves the structure to these points and then steps on from there. I find that kinetic damping invariably will get to the end results, but it can be slow. So if the viscous damping is struggling to converge, I often change the damping method during the analysis to the kinetic damping. Once the results are then sort of converging nicely, I might switch it back to viscous damping to encourage it to get to the answer more quickly. What does damping do? Well, deflections without damping would just oscillate backwards and forwards. And what we're looking for is a thing called critical damping, which is just the right amount of damping to make the structure converge in the shortest time. If the damping is a little bit smaller than critical, it will overshoot and come back. If it's larger than critical, it will take a long time to get there. And what GSA will be doing is constantly adjusting the damping to try and get this convergence as quickly as possible. Though there are times when it struggles and you have to take control. Now, for example, GSA Projects, there's a whole host of ones. I've just picked out a few could be of interest, dealing with the non-linear aspects of GSA. So here's Khalifa Stadium. You can see you've got the cable nets will be ties originally in the original model, either supporting this fabric structure, and there's straight cable nets on the other side, possibly supporting lights or cameras or whatever. Singapore Flyer, and I think I'll need to add in the new Las Vegas equivalents as well, these Ferris wheels. Khalifa Bridge in Brisbane. This is a cable stayed tensegrity bridge, which we have a case study of this on the main website if you're interested. It's not quite as chaotic as it looks. It does look quite chaotic. It is quite a logical structure, really. Then the recent London Olympics. Mott McDonald's used GSA for the fabric cladding of the shooting gallery. Expedition used GSA on their award-winning velodrome, in particular here. If you think about the cable net roof, won the Ice T Supreme Awards 2011, and of course the Bureau Happold designed main stadium for both the locked-in stresses in the compression ring, but also the cable net roof and cladding, fabric cladding supporting the lighting rigs, and so on. Also won a number of awards. So at that point, I'll throw the floor open to questions. If you do have any questions, do please type them into the box there.